Today we look at our final section discussing confidence intervals, and this is section 7.3. So if you recall from section 5.2, the probability of success on a single trial of a binomial experiment is p. The probability is this probability is a population proportion. In this section, we learn how to estimate a population proportion p using a confidence interval. As with confidence intervals for mu, we start with a point estimate. So if you remember in 7.1 and 7.2, we were working with confidence intervals for the population mean. Now we're going to switch over to confidence intervals for the population proportion. So point estimates for P and Q. Well, for P hat, which is our point estimate for P, that would be R over N, where R is the number of successes and N is the number of trials. And so Q hat was just going to be 1 minus P hat because P hat plus Q hat has to be 1. Constructing a confidence interval for a population proportion P is similar to constructing a confidence interval for population mean mu. We start with a point estimate and calculate the maximum margin of error. If you remember maximum margin of error, we always called that E. So the margin of error when using P hat as an estimate of P is P hat minus P in the absolute value. So we're just interested in the magnitude of that. And that's the same as what we had before. Remember with margin of error, when we were using X bar was X bar minus mu in the absolute value. So it's the same concept as before. So the maximum margin of error E is defined this way. So this is a new formula for us. Now, in case you're thinking, well, Kurt, that's great, but I sure would like to see where that came from, then this next note is for you. So in section 7.1, in the notes, you went through the algebra to see where the maximum margin of error came from. And there's a very similar argument algebraically on page 388 and 389 in the book. So if that wasn't enough algebra for you in section 7.1, you can look in the book and you'll see algebraically how this is developed. And then we've got another note here. And this is probably the more important one for us, this note. Put a little red star here. This note says, if NP is greater than 5 and NQ is greater than 5, then the P hat distribution will be approximately normal. So this is sort of like, if you remember before in 7.1 and 7.2, we had to check constantly that n is greater than or equal to 30, right? It's the same sort of requirement. Now we have to check this and this. So when we're dealing with proportions, we don't need this one anymore, not for proportions. For proportions, we need to check these two. NP has to be greater than 5 and NQ has to be greater than 5. And when they're both greater than 5, we have what's called a large sample. And then the P hat distribution will be approximately normal. So we're back to using z-scores, right? Normal. So if it's approximately normal, that means we can use inverse norm, normal CDF, z-scores, all the things we learned in chapter 6. So instead of checking this requirement like we did in 7.1 and 7.2, in 7.3 we have to check these two. NP has to be greater than 5 and NQ has to be greater than 5. When they're not greater than 5, we have to use other techniques which are not covered in class. So they'll have us verify this, but in our case, these will always be true. Now, if you were paying attention to that and you're not too sleepy, I know these videos, it's just not the same as being in class. These videos, I don't know how you guys stay awake during these videos, to be honest with you. But for those of you who are still awake, you might notice something about checking these. And you might say, well, how do we check this if we actually don't know what P and Q are? Well, that is a problem. The theory says that if these two things are true, then the p-hat distribution will be approximately normal. But we can't check these because we don't know P and Q. So here's how we deal with this. This is our little technical difficulty. So in most cases, we will not know the actual values of P or Q. So what we do and what everybody does in this case is we use our point estimates, P hat, which we're hoping is approximately equal to P, and Q hat, which we're hoping is approximately equal to Q. So we're going to, instead of using P and Q, we're going to use P hat and Q hat. And we'll also adjust our formula for E, for the maximum margin of error, accordingly. So here's the key to this. For NP greater than 5 and NQ greater than 5, the p-hat distribution is approximately normal. Since we don't know P or Q, we will verify that NP hat is greater than 5 and NQ hat is greater than 5. And here's the argument that we're going to use. For the samples that we look at, NP hat is going to be a lot bigger than 5, and NQ hat is going to be a lot bigger than 5. And our argument will be this. Since NP hat is a lot bigger than 5 and NQ hat is a lot bigger than 5, then most likely NP and NQ would both be greater than 5. So for the examples we see, when we plug in N times P hat, we're not going to get 6 or 7. If we did, we wouldn't use these techniques. We're going to get something like, 100 or 200. We're going to get huge numbers. So if NP hat is 100, then NP most likely is greater than 5. Because remember, our sample statistic we're hoping is close to the population proportion, right? So P hat should be close to P. So that's the argument we're going to use, and that's pretty much the argument everybody uses, because we can't actually verify these two. So we're just going to verify these, and for us, these will be much bigger than 5. So that's what the note here says. If NP hat and NQ hat are both significantly greater than 5, then NP and NQ are likely also greater than 5, since P hat and Q hat should be close to P and Q. So that's the argument we will use to be able to check these. We'll check these instead. One more thing I should mention, whenever you're testing for a population proportion, we always use these scores. Always use these scores here. So sometimes what happens is students will be introduced to students T and using T scores, but we only do that in 7.2 when we are trying to estimate the mean and we don't know sigma. So when we're back to proportions, everything is z-scores. So you want to get that stuck in your memory. If we are dealing with population proportions, we're using z-scores. That's going to be true right here in 7.3. And also in Chapter 8. Chapter 8 is kind of a repeat. Like 7.1, 7.2, and 7.3 are going to be very close to 8.1, 8.2, and 8.3. So in 7.3 we use proportions, in 8.3 we use proportions, and in both cases we always use z-scores. So if you're dealing with proportions, you're going to use the standard normal curve and z-scores. So if you look at the confidence interval for P, it looks fairly similar. We've just swapped out what we had in 7.1 and 7.2. We get rid of the X bar, replace it with P hat. We get rid of the mu and replace it with P. And of course we've got our new formula for E. And you can see we made that adjustment because we don't know P and Q. We're going to use P hat and Q hat to find our maximum margin of error. And notice also Z-scores, right? Our critical value. And this we'll use that little table again that we used in 7.1, or you can use inverse norm, but the little table where you find z-scores based on your confidence interval can be used again in this section. So we have to be able to get this estimate, this p hat. So when you look at the problems, there's going to be two ways they can do this. So there's two ways to give p hat. I'll just mention this sort of off to the side here. Two ways to give us p hat. And by this I mean like when you're reading the homework problems. So here's one way. One way they'll just come out and say p hat equals, and they put some number in there. Or they'll say something like 38% of respondents said they were going to vote yes on proposal C or whatever. So then we would have p hat equals 0.38. So they'll give us p hat like that. Or the other way to give us p hat is they won't tell us p hat, but they'll say R equals N equals. So let's say the survey was conducted where 1,500 college students were asked whether they love statistics or not. Now, we know that if that were the question, all 1,500 would say yes. But just to make it work for us, they'll say something like 1,275 said yes. So then we can build p hat from what they gave us. So they gave us the number of trials, the number of successes, and then we build p hat. And we get it that way. So when you work on the homework problems, there are these two ways. Just look at the wording. They might come out and tell us p hat, or they'll give us R and N and we can construct p hat. So those are the two ways that these problems will give us p hat. When we look at example 1, we'll see right away what I was talking about. So example 1 says, let P represent the proportion of all judges who are introverts. This is a problem right out of the book, by the way. It's number 12. P represents the proportion of all judges who are introverts. Find a point estimate for P. Remember, point estimate for P, that's p hat. Point estimate for P is p hat. So we can find it from looking up here. So they're giving it to us in this second way here. They're saying in a random sample of 519 judges, it was found that 285 were introverts. So number of trials, number of successes, right? The success is the thing that we're looking for. We just count them. So p hat is going to be equal to 285 over 519, or for the decimal fans, approximately 5491, right around 55%, right? So that's how we get p hat. And then it says find a 99% confidence interval for P. Give a brief interpretation of the meaning of the confidence interval you have found. And of course, the interpretation is always the hard part. For building the confidence interval, we just have to use our formula here and then find E. So to do that, we could say, first of all, it's a 99% confidence interval. So we need a z-score that corresponds to that. So for a 99% confidence interval, just like in section 7.1, we can look in that little table and we get our z-score is 2.58, or our critical value is 2.58. So just in case you forgot, this is what I'm referring to. This sits in the inside cover of your book, or wherever the standard normal curve or the standard normal table is in your book. This will usually be there next to it. So for level of confidence, again, we normally have either 99%, 95%, or 90%. And here are those critical values or the z-scores that we need. So for us, we need 2.58. So from there, we can figure out what E is, what our maximum margin of error. So E is going to be, from the formula above in the little box here, we've got 2.58. And then we have a radical here, and we've got p hat times q hat. P hat we already figured out was 0.5491, roughly. So then q hat, well, I'm just going to write it down, 0.4509. And now the question is, how did I get q hat? Remember, p hat plus q hat has to be 1. So q hat is just 1 minus p hat. So whatever you have here, subtract it from 1 and you'll get here. So q hat is 0.4509. And then we divide by n from the formula, and n is 519. So if you do a little work on your calculator, you should get E equals 0.0564. And once we have this, then we can build our confidence interval. So our confidence interval is p hat minus E is less than P, which is less than p hat plus E. And p hat we found out was 0.5491 minus 0.0564. It should be less than the population proportion P, which should be less than 0.5491 plus 0.0564. And if you do the arithmetic here and then clean it up, I'm just going to round it to 2 decimal places, and this is what I get. So it looks like P, we believe P would be between 0.49 and 0.61. And remember, that is just from this one sample. If we took another random sample, even if we use 519 judges, exactly the same number for n, we're probably not going to get exactly the same number here, right? So that means our p hat would be a little different. That means our q hat would be a little different, which would make our e a little different. So this would be different, that would be different, that would be different, that would be different. Right, so remember, these confidence intervals are not written in stone, they're based on a sample. And we're hoping that this sample is kind of a common sample. We're hoping it's not some weird outlier, but we don't know, right? We're making a 99% confidence interval, which means that if we took a sample like this 100 times and constructed 100 confidence intervals, 99 of them would actually capture the real population proportion. Is this one of those? We can't say for sure. All we can say is we're 99% confident that this captures the population proportion, because of the technique we are using. We'll give a correct statement 99 out of 100 times. So for the interpretation, I'm going to start mine off the same as before. I'm just going to say we are 99% confident. Right, and one more time I'll mention that this is a mathematical statement. It's not a figure of speech. It's a statement about the process that we're using. So we are 99% confident that the interval 0.49 less than P less than 0.61 is one that contains the population proportion P, we don't want to stop here because they want us to write this in the context of the problem. So we don't want to just say population proportion P. We want to also state what this is. So what is population proportion P? Well, in this case, it's the population proportion of judges who are introverts. So I'm just going to say of judges who are introverts. So you don't have to use wording exactly like this, but it should be similar. And also, here's something that happens sometimes. I'll see a lot of times in 7.3, population mean mu, just out of habit. So we're so used to doing population mean mu. but this is a proportion, right? Population proportion P. So be careful of that. 7.3, population proportion P. Also, there's no standard deviation, right? We're not talking about the mean anymore. So in 7.3, it's the same concept as 7.1 and 7.2, but we're estimating the population proportion P. Another thing that happens sometimes is students will write sample proportion P hat. Well, I know our sample proportion P hat is in here, right? If I replace this with a P hat, because P hat, if you look at what we got for P hat, we got 0.5491. That is most definitely in here because that's right in the center. So we're not trying to approximate the sample proportion. We already have that from our sample. We're trying to estimate the population proportion P using the P hat from our sample. Okay, so it's just some things that can go wrong sometimes. Just like before, we have to check the requirements to make sure that we can use the normal distribution and z-scores. So we have to consider, do we think the conditions NP greater than 5 and NQ greater than 5 are satisfied in this problem? So here's what we can do. We don't know NP, right? We don't know it, but we think it's close to NP hat. And we do know NP hat because that's going to be 519 times P hat, which was 0.5491. That's going to give us about 285, which is definitely greater than 5. So NP hat is 285, it's definitely greater than 5. You do the same thing with NQ. We don't know NQ, but we think it's probably around the same as NQ hat. And NQ hat, well, N is 519. Q hat is 0.4509, roughly. If we multiply those two together, we get about 234, which again is greater than 5. And these are both much greater than 5. So if NQ hat is 285, NP is probably greater than 5, right? And we can make the same argument for NQ. So I just wrote our argument down there. It's the one that we talked about before. Just the fact that since NP hat and NQ hat are significantly greater than 5, right? 285 and 234, then it's likely that NP and NQ are also greater than 5. And then it says, explain why this would be an important consideration. It's important because if these two conditions are met, if NP is greater than 5 and NQ are greater than 5, then the P hat distribution will be normal. So that's the important part. So the important part is the P hat distribution will be normal, right? As long as these two conditions are met. And so that means we can use everything from chapter 6 when we are working with this problem. Just like before, there's a way to do confidence intervals for the population proportion on the calculator. And again, this is just to check, right? Because we have to be able to create these from scratch, basically by calculating the maximum margin of error and then building our confidence interval. But if you ever wanted to test or just to check it, you go to the stat button, go over to tests, stat button, go over to tests. And then this time you have to look, it's a ways down there, but it's called 1 proportion z interval. So this is the one we would look for. It's a confidence interval using z-scores and it's proportions. And there's one independent variable. So this is the one that we would go to. And remember that the calculator is going to use x instead of r. So we'll have like a x, we'll have an n, and we'll have a confidence level. We have to input these values. Just remember with the x, that's what we're calling r. Our book uses r. The other variable that's used sometimes is x. On the calculator, we go to the Stat button and go over to Tests. There's quite a few of them. What you want to do is be careful you go to the right one. So if you go down here, don't stop here. We don't want this one. We want one proportion z interval. So keep going. And this is one we want. One proportion z interval. And then the calculator uses x for the number of successes. So we had 285. And the number of trials, we had 519. Confidence level, we want a 99% confidence level. Then you go to calculate, and it does all the work for us. It gives us p hat and gives us our interval. So that's how you can check your answer on the calculator. Sometimes we have to determine the minimal sample size for estimating p, and there are two cases when dealing with proportions. The first case here is used if we have a preliminary estimate for p. So then we would plug this in right here. This would be our preliminary estimate. And that could be maybe from the result of a previous survey. So we have some idea about what we think the population proportion is. And then we use that, plug that in here, and then this would be 1 minus p, which is another word for q, right? Written p times q. And sometimes you do see it like written like that. So that's case one. Case two, you don't have a preliminary estimate for p. And then instead of this p times 1 minus p, we have 1/4. You see the rest of it is the same. This part is the same here. The 1/4 comes from the fact that if you don't have this, then the worst case scenario would be 1/4, which means that's the maximum value of p times 1 minus p. So the maximum value of this is 1/4, and you can see it if you think of it this way. Think back to the good old days. I'll do it in two ways. First, I'll show you algebra. Think of the good old days in algebra. If you had this equation, and then if you were going to distribute this x through, you could say this is y equals x minus x squared. And from algebra, you would have learned that this being the second degree equation, this is a parabola. And because this lead coefficient is a -1, it's a parabola opening down. So it's going like this. And the x-coordinate of the vertex of a parabola is x equals -b/2a. So in this case, the b, if you wrote this out in ax squared plus bx plus c, the a would be the -1, the b would be +1, the c would be 0, so you would get x equals -b, which would be -1/2a, which is 2 times -1, which would be 1/2. So the vertex is at 1, the x-coordinate of the vertex is 1/2, and to find the y-coordinate, which would be basically the value here of this, you'd plug in 1/2 in here, and when you plug in 1/2, you'll get 1/4. The 1/2 minus 1/2 squared, which is 1/4, so 1/2 minus 1/4 is 1/4, which is where that comes from. And then if you've taken calculus before, we'll start from this same spot here. In calculus, if you have this graph and you want to find the maximum value here, you guys who've taken calculus will remember we take the derivative of that, set that equal to 0 to find the critical number. And when you do set that equal to 0 and solve for x, you once again get 1/2, and then you plug in the 1/2 into the original equation, you get 1/4. So all this stuff is optional. You don't need to know it, but that's where this 1/4 comes from. It's the maximum value of p times 1 minus p. And so if you don't have any preliminary estimate, you have to assume the worst case scenario, right? So you put 1/4 here. So that's where it comes from. In both cases, E will be a specified maximum margin of error. Just like in 7.1, when we had these for on the Chapter 7 handout, we had minimum sample size for estimating mu. Now we're estimating p. And in both cases, they'll give us a maximum margin of error. And then just like before, just like in section 7.1, if n is not a whole number, we don't round. We automatically increase n to the next highest whole number. So that's just the same as before. So if we plug all the numbers in here and we get like n equals 27.2, that means we need 27.2 samples, right? It's a sample size. Well, a sample size has to be an integer. We can't take 27.2 samples, so that means we need 28 samples. So we're not rounding, we're moving up automatically. So let's try one of these out. So page 396, number 10, this is from the section 7.3 homework. It says, what is the minimal sample size needed for a 99% confidence interval? So let's write that part down. We've got a 99% confidence interval. And we have a maximum margin of error of 0.06. So E equals 0.06. And then part A says a preliminary estimate for P is 0.8. So to answer this question, we first just have to know what they're asking. They want to know the minimal sample size, right? And we're talking about, in this case, P, not mu, but P. So we would look at our formula, you know, on the Chapter 7 handout, or in this case, I'll look right here. But we have a preliminary estimate. So that means we're going to use this first one. You have a preliminary estimate, so we're going to use this formula right here. So go back down here, and we can say n equals P, which is 0.8, right? That's our preliminary estimate, 0.8. Well, then 1 minus P, 1 minus 0.8 is 0.2. Right, if this is P, this is going to be 1 minus P. 1 minus 0.8 is 0.2. And then we have to realize that it's a 99% confidence interval. So using that, again, that little table that we use to get our z-scores or our critical value. If you look at that table, you'll see that this gives us a z-score of 2.58, right, for the 99% confidence interval. So we put 2.58 up here, and E, the maximum margin of error, was given as 0.06, which goes there. Then we have to square this. And if you punch this in the calculator, you get right around 295.84, which means we need 296 samples, right? That's a minimal sample size required. So 296. And remember, I'm not rounding. I'm just moving up to the next one no matter what, right? No matter what this decimal point is. This decimal 0.84 could be anything. Could be 0.04. We still move up. So 296 samples. So part B, this says that in this case, there is no preliminary estimate for P. So you've got no preliminary estimate. So just think about what this is saying. In this part, we knew a little bit about P, right? We had a preliminary estimate made from a survey done a couple of years ago. So we have some kind of idea what we think P is. We needed 296 samples. Now in this case, we have no preliminary estimate for P, which means we're coming in with less information. So if we have less information, do you think we're going to need more samples than this or less? Hopefully you're thinking, well, less information, we're going to need more samples, which is always going to be the case. And you can even see it in the formula, because when we plug 0.8 and 0.2, it's always going to be less than or equal to 1/4. In fact, the only way it equals 1/4 is when it's 0.5 and 0.5. So 0.8 and 0.2, whatever, if you multiply that out, it's going to be a number less than 0.25. So 1/4 is the biggest. It's a maximum, which means that this n is going to always be bigger. So if you don't have any information going in, you're going to need a larger sample size, which even just makes sense intuitively. So here we would say n equals 1/4, and all the rest is the same, 2.58, 0.06. We square this. If you punch this in your calculator, you should get right around 462.25, which means in this case we need 463 samples. And then you can see when you compare these two, when we come in with less information, we need more samples. So just to make it really clear, this is saying that 462 samples is not enough to guarantee that, right? To guarantee that level of accuracy. So we need 462.25, but of course it's a sample size, so we can't get 1/4 of a sample. So that's how we always go up to 463 in this case. Another thing that this section has us do is, instead of doing the, interpreting the results with the very structured and formal stating the results, they're going to have us actually talk like a normal person, like you would see on the news. So this is what this part is getting us ready for. So interpreting results from a poll. When a poll states the results of a survey, the proportion given is p hat, which is the sample estimate of the population proportion. So basically that's the result of their survey, right? They're going to report p hat, but they're not going to say p hat, and they're not going to talk about a sample statistic. They're going to use normal words everybody understands. Also, in the vast majority of polls, a 95% confidence interval is used. But again, that will never be mentioned because the vast majority of people don't understand what that even means. So we're going to learn how to say this the way that you would hear it reported in the news. But one thing you can know is that whenever there's a poll result, it's almost always based on a 95% confidence interval. So remember the ones that I said we'll see normally are either 95%, 99%, or 90%. The ones that are normally used when you get the poll results from the news, or Gallup gives survey results, they're almost always using a 95% confidence interval. So this is just saying that how we have like p hat minus e is less than p, which is less than p hat plus e. Well, we could write that this way. We could say the poll result, which would be p hat minus the margin of error, is less than p, the population proportion, which is less than the poll result, which would be the p hat plus e. So these two statements really are equivalent. This is how we have been doing it. Now we're just saying that if we swap out p hat with a poll result, we have the same confidence interval. So after you listen to the news, where they give the results of a poll, they're going to say it differently, but we could plug it in here and come back with the same way we have been doing this. So we'll see how to do that in just a couple minutes. Probably the best way to see how this works is just to look at one of the homework problems. And I'll walk you through one problem, all the steps, so you can see how these need to be done. So this one is from problem number 20, and they're talking about bargain hunters. And it says, in a marketing survey, a random sample of 1,001 supermarket shoppers revealed that 273 always stock up on an item when they find that item at a real bargain price. So they would have to define that some way that it can be measured. And this is referring to a problem from the homework just above it, problem number 19. So part A says, Let P represent the proportion of all supermarket shoppers who always stock up on an item when they find a real bargain. Find a point estimate for P. Well, we know point estimate for P is P hat. And in this case, they're giving us a way to calculate P hat. They didn't give it to us directly, but they told us that 273 out of 1,001 shoppers stock up on an item when they find a real bargain. Again, they would have to define that somehow, like maybe 30% off or more, but that's not important for us. So P hat, if you write this as a fraction, is 273 over 1,001, or roughly 0.2727. So remember, the other way they could have given us this, sometimes they'll say, in a survey, 27% of shoppers say they always stock up on an item when they find a real bargain. So in that case, they would have directly given us P hat. They would have said 27%. So just be aware, sometimes they'll give us P hat that way, and sometimes they give us P hat this way, where they tell us R over N, and we just calculate it ourselves. So this is what we do here. And since we have P hat, I'm also just going to calculate Q hat. So if that's P hat, that implies that Q hat, which is 1 minus that, or you could think of it like this, it's going to be 728 over 1,001, right? Because if 273 do stock up, that means 728 don't stock up, right? And that would be about 0.7273. And again, the other way you could get this number is go 1 minus this, right? 1 minus this works too. Or even going from the exact value, 1 minus this will give you this. So either way, we get P hat and Q hat. Part B says, well, actually, just to make it clear, this is the point estimate for P. They didn't ask us to do this for part A, but we're going to need Q hat, so I'm just getting out of the way. But this is the point estimate for P, right? So then part B says, find a 95% confidence interval for P. Give a brief explanation of the meaning of the interval. Okay, so 95% confidence interval means our z-score will be, some of you may have this memorized already, 1.96. Right? Sometimes if you're doing all the homework problems in 7.1 and 7.2, and you're following along with 7.3, after a while you'll sort of memorize these. So 95%, 1.96, right? Again, that's from that little table. So then we can just put the pieces together. P hat minus E is less than P, which is less than P hat plus E. We need to find E. Get Z sub C, P hat, Q hat over N. So you plug this in, 1.96. So P hat is 0.2727. Q hat is 0.7273. N was 1,001, and don't forget to take the square root. When you go through all of this arithmetic, you should eventually get 0.0276. So that's our margin of error. Or as a percentage, you would say it's 2.76%, right? So E is our maximum margin of error. And then we can build our confidence interval because we've got everything we need. We've got P hat, we've got E. So we just plug in the values. We will get 0.2727 minus 0.0276 is less than P, which in turn is less than 0.2727 plus 0.0276. So if you do the calculations and round to 2 decimal places, you can pretty much round where you want to unless the book tells you. But if you do it that way, we end up with this. So we say, so 0.25 is less than P, which is less than 0.30. And then if we want to give a brief explanation of the meaning of the interval, as they ask, we would say this the same way we have been saying these. So I'm going to first do this the way we've been doing it all along. We would say something like, we are 95% confident, or there's a 95% chance, something like that, that the interval 0.25 less than p less than 0.30, that interval right there is one that contains p, and maybe, I think I'll try to be more consistent. Again, this doesn't have to be exactly worded exactly like this, but I want to just be consistent. So let's say contains the population proportion P of shoppers. And now I'm just looking back at the book's wording. Like, remember, we want to say, what is this P? Population proportion, what is it in this problem? Well, it's the population proportion of shoppers who stock up on an item when it is a real bargain. Okay, so that's how we've worded it in 7.1 and 7.2. All right, it's the same wording as before. We start off with this. We are 95% confident. Then we say that the interval, the one that we found, is one that contains in 7.1 and 7.2, we'd say the population mean mu. 7.3 would say the population proportion p. And then the rest of it is just explaining what that is. So nothing new there. But here's what's going to be new, part C. Okay, here's where, I'm going to put a little red star here, so we're careful. This is the new part. This says, as a news writer, how would you report the survey results? And that also says, what is the margin of error based on a 95% confidence interval? So, one thing we need to know for this is we still have to mention everything, but we're going to use normal words like you would see if you were watching the results of a survey or the results of a poll on the news and they were reporting it. So here's what we need to know. So news people mention the point estimate. They're always going to mention that. They're going to mention the point estimate, but not going to say p hat or point estimate or anything weird like that, like we've been talking. But they will mention it and the margin of error. Both as a percent. So when you see it on the news, they're going to always use percents. They're not going to talk about decimals or anything like that. So here's what we could say for this. So when they say, as a news writer, how would you report the survey results? Here's what they're looking for. As a news writer, we'd say something like this. Based on a recent study, and we're going to mention the point estimate and also the margin of error. So based on a recent study, here comes the point estimate. 27.3% of shoppers. Now, if you're wondering where did this come from? Well, isn't that just p hat as a percentage? So we're going to mention p hat, right? We're going to mention p hat, the point estimate p hat. Margin of error, E, we're going to mention that too, both as a percentage. Based on a recent study, 27.3% of shoppers stock up on an item when it is a real bargain. Okay, now if you ever hear the results of a study or a survey and they don't give the margin of error, it's totally worthless. I've never actually heard anybody do this, but it would be totally worthless, because what if your margin of error is 80%, right? Then it makes the results almost meaningless. So they should always mention the margin of error. And like I said, they always do. Any credible news place would always mention the margin of error. So we say something like the study had a margin of error of, now usually they just round this to the nearest percentage. For this one, I'm just gonna have one decimal place here. But usually they're gonna say 3% on the news. I think I have heard them use to the nearest tenth, but they don't get very precise with the margin of error. But look what we've got. We've got everything that we had here. When we say it this way up here, that we've been doing it all along, well, people don't talk like this on the news. You never watch the news and the news person says, "We are 95% confident that the interval," it's not done. People wouldn't even know what they were talking about unless they just took a statistics class. So this is the way it's done on the news. Based on a recent study, 27.3% of shoppers stock up on an item when it is a real bargain. The study had a margin of error of 2.8%. So everybody pretty much knows that means that it could be this number plus or minus the margin of error. So you can kind of construct what we've got, because if you go, just to mention this, if you were to go 27.3% plus or minus 2.8%, that would give you, if you subtract 2.8% from 27.3, you get 24.5%. Then if you add it, you get 30.1%. So somebody who's listening to the news could construct this if they wanted to, and pretty much what we got. The rounding's a little different, but it's pretty much the same thing. So that's just because we're rounding here to the nearest tenth. So the thing that is misleading, that people don't understand, is when people hear this result of a survey, they think for 100% of the cases, the real answer is in here somewhere. What they don't understand is it's probably true. It's based on a 95% confidence interval almost always. So what it means is 95 out of 100 times this will be a true statement. But people tend to just think that it's pretty much this. This is pretty much the exact answer. But we know better, right? We know it's not. This is just from one survey, from one study. Another study would have given us a little bit different p-hat. So this is how they want us to write it, though. So in the homework, when they say as a news writer, this is what they're looking for. As a news writer. Basically, write it like a normal person talks. That's what they're saying. Write it like a normal person talks, and in a way that people who haven't just taken statistics would understand. And that's pretty much right here. And just notice we're still going to mention p-hat. We're still going to mention E, but they're going to be as a percentage in this case. So, hope you are not too sad, but that is the end of everything we do with confidence intervals. So make sure to try 7.3, get comfortable with those problems. And as always, let me know if you have any questions.